All right, IED, we're going to talk a little bit about Project Gel, and this is how to go about creating the project and the deliverables that I'm going to be looking for in your individual groups. Now, keep in mind, this is to make a gel plate that whenever you pour a liquid inside of it, it will solidify and it will create basically a big solid jello block, and you're supposed to be able to pull that out easily. The biology department wants this because the plates that they're using right now are honestly really crappy and they're breaking at this point. Not only that, but they can be improved upon. So what we're going to be doing is we're going to develop a competitive modification to the gel plate that will still fit inside the machine. And I've demonstrated how that actually works in class. If you're in my class, you can look at a video of it and see how it actually functions. And I've also provided the 3D files to you. If you want to see how you can make your own modifications, it's a public document in Onshape, and it's called the original agar plate. And you can search for it, and you can make a copy of that plate to modify to your heart's content. So the biology teachers wanted 5 different things from this plate. I asked them to come up with a list of 5 different things, and they didn't disappoint me. Scientists are usually pretty good about defining specific things that they want. So they want it to, number one, work as a mold for pouring agarose gels. The temperature of melted agarose can be up to at max 100 degrees Celsius. It's pretty much just mixed in with water. Don't think it gets warmer than that. It has to be boiling to melt the agarose in the water itself. So our mold, whatever we create, needs to be able to hold 100 degrees Celsius water or cooler, but it shouldn't be able to melt, and hopefully the plastic will be able to do that. We're going to test it and see. Uh, Number two, it needs to hold the agarose gel while running electrophoresis on the gel. So we'll see if we can actually run a voltage through it without getting it to degrade in any way, shape, form, or fashion. It'll be interesting to find out if it actually works or not. Be able to remove the gel and place the gel in without having to handle the gel too much. In other words, slide in and out without having to really lift it up or down. You don't really want to touch the gel, or you want to touch the gel as little as possible because it does alter and mess with the conductivity, and the oils in your fingers do make a difference if you're not using gloves. Hold the gel comb in place while the agarose solidifies so that the wells will be formed for inputting the DNA samples. So they came with these little combs, and those combs have to fit with whatever we're going to make. They can't just order new ones. Either that or we'd have to make new combs, and I really don't feel like it. And would also like a way to end caps to seal off when pouring gels. It'd be great to not have to use masking tape. So the plates that we have these like holes in the side, and they have to use masking tape to get them to go in the right spot. Not that good. The constraints that we have right now is that, we really can't go past the dimensions of the original design. You can't really make it go taller or wider because it has to fit inside the machine. So anything that we do to it, we're going to have to work within the dimensions that we have. And it must be made out of flexible filament or thermal polyurethane. All right, so here's what I want from you guys. Whenever you're going to go through the engineering process, just like we do in every single IED class, for the first thing is define the problem. So for defining the problem, what I'm going to be wanting from you mainly is a design brief. And inside that design brief should include a problem statement, a design statement, and then constraints, which were listed above, and requirements, which were also listed above. So defining the problem shouldn't really be that difficult for you guys because it should be fairly self-explanatory since this project was given to us. We don't really have to come up with making our own. For generating the concepts, I want concept sketches. I want ideas, and I want to be able to see those ideas. I want visual confirmation that those ideas exist. I'm not just going to take, oh, well, we thought of some stuff. I mean, like, oh, really? You did? What did you think of? Stuff. Yeah, no, I want concept sketches. So, whenever you brainstorm, come up with some ideas and sketch those ideas. And then after that, I want you to select those ideas, and I want you to select the right idea using data. So, in other words, I want you to use a decision matrix. I want you to think about your design, and I want you to, based on a specific criteria that you're going to set, I want you to make your own decision on which one is the one that you're going to do. So I want a concept sketch and I want a justification of the idea that you selected, just like always. For developing the solution, I would like a 3D model of the file, and I would also like an assembly file if you are making more than one piece. So you need the assembly file to show me all of the different pieces and how they actually fit together. For constructing and testing, I would like the teams to make a 3D printed product to be printed out. You don't want to wait till the actual deadline day to 3D print this because it's going to take a while to 3D print, and if everybody tries to do that, you're going to be too late, and you're going to get a late penalty on that. So I would highly recommend that you get that done sooner rather than later. Don't just wait till 3D print on the very, very last day. For evaluating the solution, once you get a 3D printed product and test it out, you're going to evaluate it by performing a leak test, a fitting test, and a temperature test. And to be honest, I'm pretty sure we can actually put that up with construct and test. And then the evaluate is going to be like the data that comes from your leak test, your fitting test, and your temperature test. So the testing part is actually physically doing it. Evaluating the solution is going to take those tests, that information, and you're going to either have to tweak your design or you're going to have to say, well, it's good enough. It fits within parameters, and you're going to have to justify in your evaluation why it fits within the parameters. You can't just be like, well, it's good to go. You're like, well, what makes it good to go? You're going to have to tell me. So does it pass the leak test? Does it pass the fitting test? Does it pass the temperature test? Okay, if you're virtual, obviously you can't make a 3D printed product, and obviously you can't evaluate the solution. Just try to evaluate it as best you can based on your 3D model if you are a virtual student, and I will mark you exempt for the construct and test part. Um, for presenting the solution, each group is going to need to make a presentation video recording. I have my video camera here that we can use. If you are a virtual student, you don't have access to my video camera, so I'm going to assume that technology is limited, and because of that, I will just ask for a Google Slide presentation if you are a virtual student. And beyond that, those are going to be the things that I'm going to need. We're aiming to try to have this done within about 6 days' time. So try to aim for getting all of these things done and accomplished 6 business days after you see this video. So that's the general idea that we're looking for. It may take a little bit longer. We may not meet time frames, but if Tuesday is going to be the day that we're going to be aiming for, and anything past that day, I'm going to say will suffer a late penalty. That's all I really have for you guys today, and hopefully I'm going to get some good videos of how these things actually work out, and I will talk at you guys later.